everybody. My name is Liran. This is Alex, and we are going to present to you today about KVM ASI, where ASI stands for Address Space Isolation. So who are we? Just a short introduction. So I'm an architect at OCI, which is Oracle Public Cloud Offering. I come with a background of cloud computing and virtual networking, and previously I've worked for many years in the cybersecurity area. I'm currently an active KVM contributor, especially around the nested virtualization, and I'm a very active Twitter user, so feel free to follow me or direct messages anytime. This is Alex. He is a senior principal engineer in Oracle Linux and Virtualization Group, and he has extensive experience in virtualization and kernel development in general. So what are we going to talk about today? So we will start with a very brief background about what is the problem we are attempting to solve, which is a L1TF hyperthreading attack scenario. But we won't deep dive into the details of L1TF because we don't need to understand that in order to understand the rest of the presentation. And after we understand the problem that we are trying to solve, we will enumerate various community attempts in order to mitigate this. And we'll analyze what did they do good and what did they do bad. And this will lead us to present a new proposal, which is KVM ASI, on how to maybe mitigate this issue. And only if time will permit, and it probably won't because we have only half an hour, I will show also a glimpse of a new mitigation we are also thinking about. So let's start with the background part. So the only thing you need to understand about L1TF in order to understand the rest of the presentation is what the primitive that it provides for the attacker. So the primitive that it provides to the attacker that you need to assume is that an attacker running code inside the guest can use this vulnerability to basically leak any host data that is currently present on the L1D cache. Now, the way that Intel tried to mitigate this vulnerability is not by doing some kind of change that prevents the guest from actually using L1TF, but instead they provided a new CPU microcode that basically exposes a new MSR that allows you to modify the hypervisor such that before every time you enter to the guest, the hypervisor, such as KVM, can flush the L1D cache just before entering to the guest. So the guest can still leak the entire L1D cache, but now it doesn't contain any more host-populated data. Now, the way that this mitigation breaks is when you consider hyperthreading. So the problem with hyperthreading is that it turns out that the L1D cache is actually shared between the hyperthreads on the same CPU core, and this creates two different problematic scenarios shown above. So one of them, the one shown here, is basically a CPU core that has two hyperthreads, and each one of them runs a virtual CPU task of a different VM. Now the problem is that while the one hyperthread populates the L1D cache with data of one VM, the sibling hyperthread that runs a different VM can use L1TF to leak that data because it's shared between the hyperthreads. So this basically breaks the security isolation between the VMs. So, and this is the first problematic scenario. So the second attack vector is that even if both hyperthreads on the same CPU core run the virtual CPU task of the same VM, then still we can reach a scenario that one hyperthread is running inside the guest, while its sibling hyperthread is currently running a VM exit handler because it incurred some exit condition. Now the problem is that the moment that the VM exit handler reads something from the virtual address space, it populates the L1D cache, and at the moment that the L1D cache is populated, its sibling hyperthread that still runs inside the guest can use L1TF to leak that data, even if the VM exit handler will flush it when it will re-enter into the guest. That will be too late. So this is basically the two attack vectors that we try to mitigate in this presentation. Now one could argue that let's just disable hyperthreading, it's a valid mitigation. So yeah, this is a valid mitigation, it works. However, it doesn't fit well all the production use cases. For example, when you consider the public cloud, applying such a mitigation will basically cause the public cloud to lose half of its compute capacity. So this leads to revenue loss, and therefore it's not a well-fit solution for all the use cases. So for the rest of the presentation, we'll assume that we want to mitigate attack scenarios, even with keeping hyperthreading enabled. So now after we understand this background, we can talk about various attempts that were attempted to mitigate this issue. So first, a disclaimer, all the things I'm going to show right now are just proposal. None of them yet been merged upstream, so just take note of that. And we already had a talk yesterday about core scheduling. So this is a mechanism that can be used to mitigate the first attack scenario that I presented. So basically, it's a new scheduler policy that allows you to group together a bunch of tasks by giving them the same, let's call it a security domain ID. And the new scheduler policy will basically guarantee that tasks that have different domain IDs will never run as sibling hyperthreads on the same core. So in our context, we can use that to tag the virtual CPU tasks of different VMs with different domain IDs. And therefore, the left scenario can never happen anymore. And we are only left with the scenario that both hyperthreads of the same CPU core runs the same virtual CPU task of the same VM. So this mitigates completely the first scenario. And therefore, from this point onward, we'll only talk about the second scenario, which is more complex to mitigate. So just to reiterate what was the second scenario, we have a single CPU core that have two hyperthreads. Both of them run virtual CPU tasks of the same VM, but one is running inside the guest while the other is running a VM exit handler. And the problem is that the VM exit handler, any read operation that it does, it reads something from the virtual address space, and it populates the L1D cache. And at the moment this data is populated to the L1D cache, it's leakable by L1TF from the sibling hyperthread that still runs inside the guest. Now, one could argue that the VM exit handler should access information that is only relevant for this VM anyway, and therefore this is not an issue. However, if you consider speculative execution, this is not true, because think of it, consider the case that the VM exit handler have an if that checks if some read operation is going to happen inbounds, and if it's that true, it will do the read operation. Now, the CPU can mispredict this branch and do the read operation anyway in a speculative execution manner. And this speculative execution read will also populate the L1D cache. So it basically means that it will allow the guest to read out of bounds. So this leads us to the only conclusion that everything in the virtual address space can be leaked by this technique. And the only way that we can actually mitigate this attack scenario is by reducing the sensitive information that we don't want to be leaked from the virtual address space in which the VM exit handler executes in. So in order to follow with that idea, we first need to have a look at how the virtual address space of a VM exit handler looks like. So this is a very schematic diagram. So at the upper part, you see the user space portion, and at the bottom, you see the kernel space portion. So I just emphasize in the kernel space portions some example of things that are considered sensitive. So for example, KVM maintains lab allocations of per virtual CPU structs, which also holds the registers of the virtual CPUs. So this virtual VA region doesn't map only virtual CPU structs of this specific virtual CPU. It also maps the virtual CPU structs of other virtual CPUs on the same host. So this also will allow the VM exit handler to populate the L1D cache with context of registers of virtual CPUs of other guests. Therefore, this should consider as sensitive information that we will want to remove from the VA space. Another example is the direct map VA region. Basically, it's a VA region that maps linearly all the physical pages of the host one by one. And these physical pages also include the physical pages that are used to back the memory of other guests on the host. So of course, this should be also considered sensitive information that we don't want it to be leaked. So one example of a community attempt in order to mitigate this was XPFO. And the idea is very simple. It was basically to remove physical pages that are only used by user space from being mapped to the direct map. And it's originally aimed for a different purpose, to mitigate a SMAP bypass, because you could cause the kernel to dereference the direct map instead of a user space page. However, in our context, it can also be useful to remove the pages that are used to back guest memory from the direct map. However, XPFO currently have too high performance it. For example, we won't be able to map the direct map anymore with 1 GB PTEs, and it will result in a lot of frequent TLB invalidation. So this is just one example. Another example is another passage which is called Process Local Kernel VA region, which was submitted by AWS. Basically, the idea is that some parts of the kernel space map information that is only relevant per process. And every process has its own page table anyway. So why not take a region in the virtual address space of the kernel space and make it map differently between different processes? And the implementation is extremely trivial. Basically, you just take a PGD entry and define to it a different PFN between different tasks. However, and in our context, it can be very useful because everything that we will map in this virtual address region, we are guaranteed that will be mapped only in this virtual CPU task, but won't be mapped in the virtual CPU task VA space of other VMs. And therefore, everything that is per VM or per virtual CPU, we can make sure to map in this VA region in order to hide it from being leakable in the virtual address space of other VMs. So for example, we can map there the per VM, per virtual CPU structs, the temporary K-maps that are done during VM exit emulations, like mapping the VMCS12 during VM pointer load, or K-map in general that VS kernel backends do. And this was, after we understand this point, we can talk about KVM ASI. So basically, if you look at all the mitigation that we have just seen, basically the idea is that we look at the virtual address space that currently exists, and we try to explicitly spot things that are considered sensitive and remove it from the address space. Now, the problem is that this approach is a result of the fact that the virtual address space of the VM exit handler is coupled with the standard VA space of the entire host in general. So they try to modify the memory management of the host in general. So a different approach can be, which is what KVM ASI does, to decouple the virtual address space that the VM exit handler is executing from the standard virtual address space that standard host tasks use in kernel space. And that will allow us to create a new virtual address space that is built in a whitelist approach that we selectively choose what is mapped in that address space. And this was introduced in a last year BOF, and Alex, who stands beside me here, have done most of the implementation since then. So regarding KVM ASI, just another point about the high-level idea, and then I will pass Alex for more details, is that basically the idea is that when you provision a new VM, you create a new virtual address space that only maps the per VM information and core kernel mappings, like the KVM module, the Linux kernel module, the IDT, the GDT, the current stack, and trampolines needed for handling external interrupts. And then when you enter to the guest for the first time, you switch to this isolated address space. Now, what is interesting is that when you encounter a VM exit, you are still running in this isolated address space. And we hope that the address space was built such that the majority of the VM exit can actually be complete their function properly just while staying in this address space. And because they are executing in an isolated address space, we know that nothing sensitive can be populated to L1D cache, and therefore we don't care that the sibling hyperthread is still running inside the guest. However, some VM exits, like exiting to user space for device simulation, will still need to run in the full virtual address space. So in this case, we have no choice, but we need to kick the sibling hyperthread and switch to the full VA space and allow the sibling hyperthread to return to the guest only once we switch back to the isolated VA space. But the assumption here, again, is that the majority of VM exit doesn't need to do that, and this is what we need to prove with numbers and performance benchmarks. And another point worth mentioning is that because we know that during the VM exit handler, assuming that we didn't exit the isolated VA space, L1D cache could not be populated with sensitive data, we don't need anymore to flush the L1D cache on every VM entry, which will also improve the performance. So this is the idea in high level, and I will let Alex continue from here.
So yeah, this idea for KVM is to create a new address space. And so there was a first proposal about this idea. And there was a lot of comments saying, yeah, this is kind of similar to what we have with KPTI. When you are running the user space, you are actually part of the kernel mapped in. So it's kind of a reduced kernel address space. So we are trying to find some similarity and to merge the both of them. Because we have some explicit point where we are going to enter this isolated address space, some point where we are going to exit. This is explicit enter or exit for KPTI. That would be, for example, on the syscall. At the end of the syscall, we will enter that reduced address space and exit on the syscall enter. For KVM address space, that will be explicitly into KVM. And also, there are implicit exits when you take an interrupt or anything, or things like this, we are going to exit. And that's why we are considering, and I have some idea about merging the two, so we can provide a more generic kernel ASI and not something limited to KVM. What we need to do, the implementation, is so to have some mechanism to switch between the page table, to have some mechanism to do the transition, so to enter and to exit ASI, and some generic mechanism for the implicit enter and exit, for example, during the interrupt and exception. There's probably some work we would like to do, we need to do around the memory allocation, because we don't want, for example, to modify vast isolated address space when doing a memory allocation. Otherwise, we will have some discrepancy between the full kernel address space and this limited address space. So far, I have something working. It's not very stable, so I'm able to run an idle VM, so it works fine if you want to protect an idle VM. I've tried to collect the data. The problem is, as I cannot run some workload because it's hanging, the data you're saying are very limited and just to the boot sequence. So I start the VM, and I collect data up to the logging prompt. And what you can see is that we are able to run KVM and do the VM exit and VM enter, most of the time staying in that isolated address space. So we put the entry into the address space into the CPU enter guest. So we enter this reduced address space, do the VM enter, VM exit, process the VM exit, and when we go back, we check if we are still on this isolated address space. And that's the case in 97% of the case. Which, yeah, that was a surprising number for me. I was expecting less. I've tried also with nested VM. It dropped to 75%. I haven't investigated exactly why. So this is the main loop. So main loop, we stay most of the time. And then I've tried to break this down into the handler themselves, depending on the VM exit reason. So in that case, we are in the reduced address space. We are going to call the VM exit handler in the kernel, and I check afterward if I'm still in the reduced address space. And this is the case for the most common VM exit reason. So we don't take into account whether it needs to return to userland, because that's different from ASI. And so the number looks pretty good so far for what we have. And we can probably have further improvement, maybe needed by the workload also, if we need. And so this is a breakdown of the VM exit processing. Some of them are not processed at all, but you can see how this is fairly well handled for most of the cases. So the current state for kernel ASI is, as I said, there was some patches sent upstream. There was first version, which was mostly implemented in KVM. The second version provides the kernel ASI, which is more generic, so usable and provides some framework you can use for different parts of the kernel, but it's not merged with KPTI. So the next version I envision is to provide a new RFC where I have something where kernel ASI would be used by KPTI. Something we don't do also is when we exit ASI, we should notify the other sibling at other thread that it should exit the VM, but it's not something we have yet. And there's a bunch of unresolved issue. That's the stability issue I mentioned. Under load, it's hanging. It's a nasty issue. There was the issue of identifying all the different data that you need to map into that address space so that KVM can run. It was a big concern to me initially, but over the time, I've realized that's not so bad. So the way it works currently is if you are running an ESI, or something is not mapped, it's going to page fault. We are going to handle the page fault, switch back to the full kernel address space, and continue execution. And during the page fault handler, we are going to log some information where the fault occur. And for example, you've got the instruction pointer where it's failed and the stack. And that way you can go back to your code and try to identify what is missing. It's working well most of the time. We could think about a more complex solution like static code analyzer to try to find out, but that may be overkill depending. And yeah, the different approach also we can have is currently, so we are building the kernel KVM address space from scratch, so you need to figure out exactly what you need to map. We could do the different approach, which is to start with a full kernel address space and try to reduce it. This was the initial thought we had, but we eventually moved to the second solution because I think that's safer, because that's that's secure by default. And I think we would have issue if we start with full kernel address space and then try to decrease it, especially regarding memory allocation or anything that could change your address space when you are doing, if there is some mapping change into the address space. So I think Liran is going to conclude about this work. I'm just out of time.
Yeah, thanks. So just to sum up the high-level idea that is presented here, so basically we saw that L1TF has two hyperthreading attack scenarios, right? One of them was that sibling hyperthreads run basically virtual CPU tasks of different VMs, and this was mitigated by core scheduler. And then we were left with only this situation that one hyperthread is running inside the guest, while its sibling hyperthread is running a VM exit handler that populates the L1D cache with sensitive data. And then we decided to mitigate this by reducing sensitive information from the VA space. So XPFO and process local kernel VA region try to do general modification to memory management, and kernel ASI basically took a different approach of decoupling the VM exit execution environment from how the host standard task VA space looks like. And then this allowed us to build the address space in a whitelist approach, which also allowed us to not flush the L1D cache on every VM entry. And another point worth mentioning, but I won't explain in details because lack of time, is that I think that kernel ASI is the only method to mitigate the user to kernel attack, MDS attack vector when you keep hyperthreading enabled. So that's also an interesting evolution of KVM ASI. So I'm not sure how much time we have left. Okay, so I would just say that in general, that when I originally thought about the KVM ASI, I didn't consider a better mitigation that we are currently working on, which is basically the idea to not partition the virtual address space, but instead to partition the physical pages between what are used by the guest memory and those that are used by the host. And this has many good properties from a performance optimization perspective. For example, you don't need to occupy a lot of host memory pages by the struct page, but it also has nice security properties. For example, all the pages that are used in the non-X area aren't mapped in the direct map to begin with, and that's it. And all the non-X physical memory will just basically be used to back guest memory. So it will allow us to remove the problem of the direct map. And also, if every sensitive information that we want will be mapped only in process local PTs, which is either EPT or user space PTs or the kernel space VA region PTs, then it is considered safe because it's mapped only on the virtual CPU task of the specific VM. And this allows for a clear mental model that everything that holds this condition is safe and it's not leakable anymore. So this was just a glimpse to this idea. There is also a bunch of issues with that, with considering VOS kernel backends, but we don't have time to dive. You can see the slides later. And just as a conclusion, we can see that even though the problem is being worked on for a significant amount of time, there is still no public solution that is perfect for L1TF or MDS attack vector. And KVM ASI, kernel ASI in general, shouldn't be viewed to just mitigate this attack vector. In general, you can view it as a generic arbitrary read primitive mitigation. Even if for info leak that happens architecturally, you still want to prevent, in the VM exit handler, you still want them to prevent the info leak. And my personal insight about this is that, first of all, I think the KVM community should better review the work that are done on hypervisors that are outside of the Linux community, such as the work that are done in Hyper-V. And also that, in general, both mem equals X and the ASI technique, they both try to decouple the execution environment of KVM from the rest of the host. So it's for me, it kind of raised questions about the security posture in general of type 2 hypervisors. So this is all we had to say. Thanks for listening. If we have time for questions.
Like one question, probably.
So when you talk about kicking out the sibling, are you saying you're just having it migrate to, let the scheduler migrate it to another core?
So it's basically doing an IPI, right, to get it out of the guest and then block it in a KVM virtual CPU block loop. And then you will allow it to get released from the KVM virtual CPU block loop until only when you return back from the sibling hyperthread to the isolated address space.
Okay, one more. So you still have the kernel stack mapped in that limited address space. Are you sure there is nothing on there that is worth leaking?
So you are right. The virtual CPU threads stack also needs to be hidden from the VA space. It is in the isolated address space. You can make sure to map it only there. But in the mem equals x, you can make sure to back the stack in a non-x physical page and map it in the kernel space VA region that is different between different tasks, and that will also hold.
Okay, thank you.